Have you ever wondered what makes a language regular in the world of automata theory? Regular languages, a cornerstone of computer science and theoretical research, are a fascinating domain to explore. They're recognized by finite automata, described by regular expressions, and boast of intriguing properties. Whether you're delving into the intricate world of computer science or simply curious about the theories that underpin our digital world, understanding regular languages is a journey worth embarking on. Stay tuned to get a deep dive into the world of regular languages. So, what exactly is a regular language? Well, in the realm of automata and formal languages, a regular language holds a significant position. It's a type of formal language that can be recognized by a finite automaton or can be described through a regular expression. Let's break it down further. Imagine an alphabet, not the kind that starts with an A and ends with a Z, but a set of symbols that we use to construct our language. Now consider a language L that we form using this alphabet. If there's a finite automaton that recognizes this language L, we call it a regular language. Now, what does it mean for an automaton to recognize a language? Essentially, it means that this automaton accepts all the strings that belong to the language L, and only those strings. Whether it's deterministic or non-deterministic doesn't matter. This automaton will always be able to identify whether a string is a member of our language or not. So the key to understanding regular languages lies in the concept of finite automata. They're the gatekeepers, the ones who decide whether a string belongs or not. And if they give the green light, then we're dealing with a regular language. In simple terms, a regular language is one that a finite automaton can recognize. Regular languages are known for their closure properties. This means that if you perform specific operations on regular languages, the result will also be a regular language. This characteristic is a part of what makes regular languages so fascinating and useful. Let's delve into the different closure properties of regular languages. First off, we have the union operation. If you have two regular languages, let's call them L1 and L2, their union, denoted as L1, L2, is also a regular language. This operation essentially combines the two languages, encompassing all the strings from both L1 and L2. Next, we have concatenation, an operation that involves stringing together words from two regular languages. So if we take our two regular languages L1 and L2, their concatenation, denoted as L1, L2, results in a new regular language. This new language includes all the strings that can be formed by taking a string from L1 and appending a string from L2. Then there's the clean star operation, which creates a new regular language consisting of all strings that can be formed by taking 0 or more strings from a given regular language and concatenating them. If L1 is a regular language, then the clean star of L1, denoted as L1, is also a regular language. We also have complementation. If L is a regular language over an alphabet sigma, then the complement of L, denoted as S or L, is also a regular language. This operation creates a new language that includes all the strings over sigma that are not in L. The intersection operation is another closure property. If L1 and L2 are regular languages, then their intersection, denoted as L1, L2, is also a regular language. This operation produces a new language that includes all the strings common to both L1 and L2. Lastly, we have reversal. If L is a regular language, then the reversal of L, denoted as L circumflex R, is also a regular language. This operation creates a new language that includes all the strings that are reversals of the strings in L. These closure properties make regular languages a versatile tool in the hands of computer scientists. They provide a powerful framework for analyzing and manipulating strings, which is fundamental in various areas of computer science. But how do we describe these regular languages? Enter regular expressions. Regular expressions, or regex for short, are a kind of shorthand language used to describe patterns in strings. They serve as a concise and flexible means for identifying strings of text, such as particular characters, words, or patterns. At the heart of regular expressions are symbols from the alphabet we're working with, whether it's A, B, or 0, 1, or any other set of symbols. But regular expressions don't stop there. They also include special characters that represent operations, forming a pattern to match against strings. Consider three core operations: concatenation, union, and the clean star. Concatenation is just stringing symbols together. For instance, AB is the concatenation of A and B. Union, denoted by a vertical bar, represents a choice between expressions. So a B matches either A or B. The clean star, represented by an asterisk, allows 0 or more repetitions of the preceding expression. O asterisk matches A, and so on, including the empty string. Now let's combine these operations. The regular expression AB denotes the language of all strings over the alphabet. A, B consisting of 0 or more occurrences of the symbols A and B. This could match A, B, ab, bar, aba, baba, and even the empty string among others. Parentheses are also used in regular expressions to determine the order of operations, similar to how they're used in arithmetic. For example, in the expression AB, the clean star applies to the entire expression a B, not just the symbol B. Regular expressions are incredibly versatile. They can define a wide range of patterns, from simple sequences to complex structures. Whether you're trying to match a specific word in a text, validate an email address format, or pass log files, regular expressions come in handy. In the context of automata theory and formal languages, regular expressions provide a compact yet powerful way to describe regular languages. They're like a secret code, enabling us to express complex language rules in a few concise symbols. Regular expressions are a compact and powerful way to describe regular languages. Now let's talk about the heroes of our story, the finite automata. These are abstract computational models that are equipped to process input strings symbol by symbol. As they navigate through these strings, they transition between different states, guided by a set of predefined rules. There are two main types of finite automata that we typically encounter: deterministic finite automata, or DFA, and non-deterministic finite automata, or NFA. Both of these are instrumental in recognizing regular languages, but let's break down how they differ. Deterministic finite automata, as the name suggests, operate in a deterministic manner. This means for each state there is precisely one transition for each possible input. It's like a well-mapped journey with a clear, unambiguous path to follow for every symbol it encounters. On the other hand, non-deterministic finite automata have the potential to exist in several states at once. For each state, there can be multiple transitions for each possible input, or perhaps none at all. It's a bit like being at a crossroads with multiple paths to choose from, or sometimes no path at all. And yet, despite this seeming chaos, NFAs are just as capable as DFAs in recognizing regular languages. The beauty of finite automata lies in their ability to bring regular languages to life. They do this by accepting or rejecting strings based on whether or not these strings belong to the regular language they're designed to recognize. Just imagine, every time you type into a search bar or use a command line, there's likely a finite automaton working behind the scenes, making sure your inputs are recognized and processed correctly. So, whether deterministic or non-deterministic, finite automata serve as the engines that power the recognition of regular languages. They embody the theoretical concepts we've discussed and make them applicable in real-world scenarios, underpinning many of the digital systems we interact with daily. Finite automata are the machines that bring regular languages to life. What does this all mean in practice? Well, let's dive into some examples and applications of regular languages to bring this all into focus. Imagine you're working with binary strings, and you need to identify those with an even number of zeros. This is a perfect job for a regular language. By using a deterministic finite automaton, you can easily process binary strings and determine whether they meet the criteria. Another common example of a regular language is the set of all strings over the alphabet AB that contain the substring ab. This might seem like a simple task, but when you're dealing with a large volume of strings, a non-deterministic finite automaton can be a lifesaver, efficiently sorting through the data. Furthermore, consider a task where you need to verify whether a string over the alphabet 0, 1 represents a valid binary number. Yes, you guessed it. This too is an instance where regular languages come into play. But beyond these examples, regular languages have a wide array of applications in the world of computer science and related fields. For instance, in lexical analysis, a crucial step in the process of compiling, regular languages are used to tokenize or break down the source code into manageable pieces. This process helps to identify syntax errors and improve the efficiency of the compiler. Pattern matching, an essential tool in data analysis and retrieval, is another area where regular languages shine. They enable us to search for specific patterns within text or data sets, greatly enhancing the speed and accuracy of the search. Regular languages also play a key role in network protocols, helping to ensure the correct formatting and transmission of data across networks. This is critical for the seamless operation of our internet and communication systems. And let's not forget database queries. Regular languages assist in refining search parameters, enabling us to retrieve accurate and relevant data swiftly. The applications of regular languages are vast, making them an integral part of computer science. So, you see, understanding regular languages is not just a theoretical exercise, it's a practical tool that's a cornerstone of modern computing. So, we've covered a lot today. We delved into the intriguing world of regular languages, exploring their definition, closure properties, and how they're described by regular expressions. We learned about the role of finite automata in recognizing these languages. We even delved into some practical examples and applications, revealing their widespread use in computer science. It's a complex but fascinating topic, underscoring the importance of formal methods in analyzing and manipulating strings and languages. Understanding regular languages is essential in automata theory and many areas of computer science. Keep exploring, keep learning.